Don't go into a lot of detail. Of course, you need a very porous material. This is a picture of an aluminum silicate A-type zeolite, certain structure. The crystals you're looking at might be 2 to 5 microns on a face, and within that structure you will have apertures or pore openings on the order of 5 angstroms or so in this structure. So there'll be about 3,000 to 4,000 pinholes in every single dimension on the surface of this crystal that would look something like this. This is sort of the atomic view. You can see the tiny little opening here in the center. That's about 5 angstroms for this particular structure. In the X-type zeolite, that may be 7 or 8 angstroms. If you strip away the silicon, oxygen, and aluminum molecules, you can see the cage where a lot of adsorption takes place, and there's many cations. This is just a typical example of a porous material. What's interesting about separations, for gas separations anyway, is you need pores on the order of the size of the molecule, a little bit bigger, or they don't work very well. You really need the interactions with the walls to cause strong enough forces to retain the material by physisorption, but weak enough forces that you can regenerate easily with a drop in concentration or a drop in pressure, namely pressure swing. Sometimes you might have to use thermal swing. So a lot of larger pore materials, like some of the aluminum phosphate 15 angstrom type pore materials, really haven't caught on as far as gas separation techniques because the pores are too big, even though they're micropores, which are defined less than 20 angstroms. So you need some small pores. This gives you an idea of the X-type cage, where this opening now is about 7 or 8 angstroms. There's a number of cations in here. The silica aluminum structure has a net negative charge, so it's a natural ion exchanger, and you can change this opening. The difference between a 3A, 4A, and 5A zeolite is really the cation that's in there, and there's several cations within each cage. I forget offhand, but like a dozen. There's various places, and it's different in the A-type structure, in the X-type structure. Just to give you an idea, if you need a porous material, you can't pack these kinds of crystals into a bed. These are micron-sized particles, and the same thing with dusty carbon materials or dusty silica gel materials. You really have to pelletize them into something that's more manageable. Now you're in the millimeter range. These pellets may be 3 to 4 millimeters long and 2 or 3 millimeters in diameter. They could be spears, 3 millimeters in diameter, and it varies all over the gamut. You can get carbon materials that are chunks of small pieces of charcoal, anywhere from fairly small, fractions of a millimeter to several millimeters in size, and you pack those into a column. Once you get that packed into a column, now the fundamentals show up. You have to have some selectivity between the gases you're trying to separate on the particular adsorbent. I'm showing here adsorption isotherms for oxygen and nitrogen on lithium X zeolite. This is a partially lithium exchange X-type zeolite. These really are the isotherms. I've removed the points. They're at 25 degrees, and it's showing the amount of these gases adsorbed per kilogram of adsorbent as a function of pressure in kilopascals up to about 7 atmospheres, 6 atmospheres or so. And you can see the significant difference. The uptake in nitrogen for this material is 3 to 4 times greater than oxygen, which means if you expose air to this adsorbent in a very specific manner, you can produce oxygen as the light gas while nitrogen's being adsorbed. And of course, once the material is more or less saturated at the feed conditions, you have to regenerate, and we're going to get into that, and that's what this talks about. But you have to have this selectivity. It's just like a relative volatility in distillation. On the order of 2 or more, you might have something feasible. Can you do the separation with very small selectivities? Yes, but it becomes problematic and very energy intensive, and it's going to have to be something that's of very high value, like an isotope. We've actually done simulations, and there's work in the literature where selectivities of 1.05 or 1.1 are good enough to enrich an isotope, but certainly you're not going to get high purity. It's just a slight enrichment process.